I'm going to go over this problem again since I messed it up so royally in class. All right, we're going to revolve this curve around the axis x equals 1 for values of y going from 0 to 2. What is the volume of the solid generated? So we're revolving this curve around the line x equals 1. I'll use this little arrow to indicate that. So this line will rotate around x equals 1, and everything on the inside will be considered our solid of revolution. And this is our representative rectangle. And when that rectangle rotates around x equals 1, it sweeps out a disk. So the volume of the overall solid will be the accumulation of these disk volumes. As y goes from 0 to 2, we'll add up all of those disks, and then we'll take the limit as this dy, the height of every disk, approaches 0, so that the number of disks approaches infinity, and it becomes the exact volume of this surface of revolution. And each disk's volume is the area of the base, which is pi r squared, multiplied by the height, which is dy. And that representative rectangle with the differential dy tells us that these limits had to be values of y, and the radius needs to be a function of y. So for this problem, all we need to know is what's the function that represents the radius. Well, the radius is from the center of the disk to the edge, and the edge is defined by our red curve, ln of x. So from the center to here, it's going to be the x value of this point minus 1. Because if this x value was 5, then that's the distance to the y-axis. But this is 1 unit away, so 5 minus 1 gives us a radius of 4. So the radius is this x value minus 1. So what is the x value anywhere on this curve? We have to use the function that describes that curve. So the x value for any point on this curve as a function of y, if y equals ln of x, then x equals e to the y. All right, so we know our radius. The length of this purple segment, the radius of this cylinder, will be this x value minus 1. E to the y minus 1. All right, so we're ready to finish this problem. The volume of the solid of revolution is the accumulation of cylinders as the y values go from 0 to 2, and then the volume of each cylinder is pi radius squared, and that's the radius. Times the height, and the height is dy. There we have it. So we're done there, because I'm just really concerned about the setup. But we could do this with our calculator or without. Without the calculator, we can just do the antiderivative process with the fundamental theorem of calculus. And this is approximately, if you use your calculator, about 50.331 cubic units. Let's throw in one good example of a washer problem. So a washer is just a disk minus a disk, which essentially leaves us with a washer. So we can see that to find the volume of an individual washer, we just have to do the overall big disk minus the little disk in the center. This is the example I'd like to try for a washer example. Let's find the volume of the solid generated by rotating some region R around this line. This will be our axis of revolution. A region of R will be defined by the space bounded by the x-axis, the y-axis, the vertical line x equals pi over 2, and the sinusoidal curve y equals sine of x. Let's begin graphing these things so we can see exactly what region R is. so we know how to rotate it around this axis of revolution. All right, let's graph the x-axis and the y-axis as boundary points. So this will be one boundary. The y-axis is another boundary. The vertical line x equals pi over 2 is another boundary. And finally, the curve y equals sine of x, which is here. We now have our region R. All right, time to revolve this around our axis of revolution, which is the vertical line x equals 3 pi over 2. So imagine taking this red region and rotating it around the y-axis. It's like it's tethered on a pole, so we'll always keep this distance away from the axis as it rotates all the way around. All right, let's get to our representative rectangle and our representative disk. This would be a representative rectangle. If you thought this could be a representative rectangle, that would be a mistake, because upon revolving that around the line x equals 3 pi over 2, you wouldn't get a disk at all. This is not a cylinder. This is a wall. It doesn't include the inside. It's only this thing where the width is dx, and it's just the wall. It's not a disk at all. In fact, this is called a shell, and it's in section that the BC curriculum does not cover, called the shell method. So, your representative rectangle, when we use the disk method, cannot be parallel to the axis of revolution. It must be perpendicular to the axis of revolution. The representative rectangle is now perpendicular to the axis of revolution. This is going to have to be a dy problem with an integrand that's a function of y, with limits of integration that are values of y. Okay, let's draw the picture. For one representative disk, just using this one representative rectangle, if that rectangle revolves around this axis of revolution, we'll obtain this washer. Then we'll want to do the definite integral, which will accumulate all these washers from the bottom to the top. All right, so the volume of this one representative washer will be the volume of the entire blue disk minus the center disk. There's the entire blue disk, and there's the center disk that we're cutting out. So the volume of the entire blue disk is pi radius squared, the area of the circular base, times its height dy. And when we cut out and subtract the red disk on the center, it's also pi times radius squared times the height, which is dy. So we need to figure out what these radii are, the big radius and the small radius. For a big blue disk, the radius is this dimension, which is going to be just a subtraction problem of this x value, the bigger x value, minus the smaller x value. The bigger x value is 3 pi over 2. The smaller x value is defined by our green curve. So if our green curve's function is y equals sine of x, we need to know the x value right there because we're measuring horizontal values. And so the x value is the arcsine of y. So our radius will be the bigger x value minus the smaller x value. 3 pi over 2 minus the x value of any point here, arcsine of y. And we just put that in for the radius of our big disk. All right, and now we need the radius of our small disk. Our small disk has a radius which goes from here to here. So what's that small radius? The bigger x value minus the smaller x value. 3 pi over 2 minus pi over 2. Or in other words, 2 pi over 2, or just pi. Making it a little easier to read. And then, of course, if we use the formula and not the conceptual understanding of big disk minus small disk, the formula looks like this. which just simplifies what you see here to this. The big radius squared minus the small radius squared. Pi times that times the height dy. We're not going to do this one without a calculator. We're just going to stop here. So I hope that helped to clarify things a bit on the washer method. One quick thing, if you look at this one representative washer, if we move the representative rectangle up, you can see that the small disk still has a radius that is 3 pi minus 2 minus the small x value, which is still pi over 2, which is still just pi. All right, I think we'll stop there.